Hi, a lot of people ask me how did I set up my worm simulation in Houdini, and even though it's relatively simple, I think a rundown is probably will be more time efficient for explaining. So, like most projects, I started by constructing the geometry. A worm geometry is basically just one line which I construct on the z-axis just for convenience, and I add a lot of points. I need to add a lot of points because we're gonna build our worm, the body of our worm, based on the p-scale attribute of the points. But before modifying the p-scale attribute, we need to add a u attribute to the line. As of now, we don't really have a u attribute in our line, just a position attribute. So let's create a new attribute by simply dividing the point number by the numbers of points, minus 1. This is a very typical system in which you get a U attribute. After it, we get the U attribute, which if we now see the geometry spreadsheet, we see our U attribute present in the line from 0 to 1. We can manipulate the p-scale based on that U attribute. So, as you see, I created a p-scale based on the ramp here, which is linked to the U attribute that we just created. Then I added two more variables, p-scale minimum and p-scale maximum, just to fit the ramp attribute that we created for the p-scale between those two values, in order to make sure that it never goes to 0 and it never goes above a certain value that I want. In my case, for the shape of the ramp, I draw the shape of a worm. And then for the minimum and maximum scale, I use 0.05 to make sure that it's not 0, and 0.6. Once that we have this p-scale attribute, we just drop a poly wire, making sure that the wire radius is associated with the p-scale, and we will get our worm. This is the body of the worm, our beautiful worm. But we're not going to work with the worm, because that will be very heavy, and worms are basically just lines with different thickness. We're not even going to work with the original line with all the points and all the p-scale attributes. We just want to work with the reduced space of the line. However, we want to preserve the head, the first point, and the last one. Since that's the head and the tail, that will be very visible if they become shorter or larger. I will start by deleting 3 points for every 4 points, but I will leave the first point intact, starting from point number 1, not point number 0, and ending at number of points minus 1, not number of points as it's usually the case. As you can see, we have a lot less points than originally, but this should be fine for our animation, for our simulation to be precise. I add the res attribute because it's always good to have a res attribute just in case. And I will create a null called this outwire, because first we're gonna deform our worm on the sub level, but later I want this deformation to happen inside the dynamic operator, so the Dop animation simulation. Let's start first by creating our Vellum geometry. I use Vellum strings. I don't use hairs because in my case my worms are symmetric, so I don't really care about the orientation. If you do want an orientation attribute created in your simulation, you should use hair, and then extract that orientation attribute and put it in your geometry. But the problem with once that we create a Vellum object is that the p-scale gets basically reset to 0.1 or 1 according to the different systems you have. And we want to use the p-scale that we created before. So I copy the p-scale attribute from my original wire geometry into the Vellum geometry. Once that I have the p-scale attribute inside the Vellum geometry, that will be the geometry that I will use in my Vellum simulation. But since it's Vellum, we do need the constraints for this geometry. So we extract the constraint directly from the Vellum string node, and I add the rest attribute for the same reason as above. I don't know if I'm gonna need it, but it's always good to have. Now, the original wire I need to deform because right now our worm is dead. It doesn't stretch in this direction or expands its body. The expansion will be represented by the p-scale, and the stretchness will actually represent in the movement of the points. Like I said, this deformation, it will happen inside Dops, but I need to test it first here inside my geometry. So you can really deform it however you want. My system is a little bit precise, but if you want, I can just run down of what I did, and you can just copy the code and test it for yourself. Suffice to know that first, just for habit, I create two different attributes. A stretch attribute that represents how much it will stretch the body, and an expand attribute that basically represents how much will increase the p-scale to represent how much it inflates the worm. So let's start by creating those attributes, and then I use those attributes in order to actually create that deformation. As you can see here, the points move on the z-axis, and the p-scale also animates based on the expansion. To visualize this, you can just copy a bunch of single sphere into all the points, and then we have a worm that is stretching and expanding. Let's increase the expansion factor by 1 in order to visualize it better. There it is. But they don't really expand that much, at least not the worms in my garden, so I'm just going to go back to 0.1. Now, as I said, you can just copy how do I create the attributes, go over it yourself. And how do I deform the attributes? And test it for yourself. But like I said, suffice to say, this actually will happen inside Dops, not here. This is just for testing purpose. Nonetheless, I create a null called outDeform. So now we have the three nodes that we need in order to run our simulation. A geometry node with a geometry for Orbellum, a constraint node with the constraints, and a deformed node, which is the worm actually deforming. I need basically this tree because my system is based on the Vellum rest plan. As of 17.0, it was not really possible to change the rest length attribute on a per primitive basis. Now on 17.5 it is possible. Nonetheless, I find Vellum rest plan rather useful, as it is not as harsh as just replacing the rest length attribute. It kind of tries to comply with a new geometry as much as it can. Let's see this better inside Ops. But before going to Dops, I will be creating not one worm, but I will be creating many worms, hundreds of worms, thousands of worms. Again, my objective is a system that can be stable in the levels of thousands or tens of thousands, as much as your memory allows it. So for that, I want to create an emitter of points, something that gives me 1 point per frame. Now, there are many ways to do this. Let's just, to test, I will quickly create just a simple grid in the meter. I just create a simple grid with 4 points. Transform it in the y direction so they're above the ground. So they are not created exactly where the ground is. I give them a normal, not necessarily for this iteration, but the normal will help you if you want to give them different direction. And then I delete all points except the point number that is equal to the frame number minus 1. That will give me 1 point per frame. In total, I have 4 points, so I will have 1 point in frame 1, 1 point in frame 1, 1 point in frame 2, 1 point in frame 3, 4, and then nothing. But there is a little thing that you should be careful about. We want a system that is stable even if we decide to use substeps. And there is, if we actually go to our global animation properties and remove the tick in the integer frame values, we can see how the point is still present in the floating frames. We don't really want this, as the Vellum solver will try to create one instance of Orbellum geometry even in the substeps that we create. In order to delete the points in the floating frame, I simply just create an attribute wrangle that removes points whenever the rounded value of the floating frame is not equal to the floating frame value. So the rounded value of 1.2 will be 1, which is obviously not equal to 1.2. So it will remove all points then. So after that happens, you will notice that we only will have points in integer values of frames, 1 and 2, but not in between. My system, however, is stable enough that you don't really need substeps. However, I like my system to be able to expand if I wish to give them more precision by adding substeps. So I always add this little trick. So in order to later link to this output, I create a null called outEmitter. Now that we have our emitter, we can go into the Dop simulation. I'm going to start by going back to integer values of frames, expanding my timeline. The Dop simulation is your basic Vellum setup. You have the Vellum object with forces applied to the middle input and the Vellum source. In our case, we want our source to be on instance points. So we need to define the instance point to our outEmitter that we created before. The most important thing, however, is that we need to add the value of frame inside the Vellum patch name. This is in order to distinguish each of our worms. Once that we create our worms, let's disable for a second the pop win. Once that we create our worms, then we will have 4 different worms, and we want to be able to distinguish them. We do that by using the Vellum patch name. Each of these worms will have whatever value you want, in this case the value of my node, worm Vellum, and then the frame number. Remember, 1 point per frame. So frame number 1, 2, 3, and 4. This is important because once we create our worm, we need to now deform the geometry and then update the constraint geometry. We do this with two different subsolvers. First, a subsolver that is linked to the data name geometry. And then this is in order to change the p-scale attribute. So our worm actually expands its body. And then we need another subsolver in order to change the value of the rest length, which we do this by using the data name constraint geometry. This will update then the constraint geometry for Vellum. And here in each of these sub is where our Vellum patch name will be helpful, because if we go and see into our geometry, we see how inside geometry, in the points attributes, we have a value called patch name, which goes from worm Vellum 1 to worm Vellum 4. We play a little bit. So inside geometry, worm Vellum 1 to worm Vellum 4, distinguishing each of our 4 worms. The same we have in our constraint geometry. The benefit, however, is that in the constraint geometry, we also have inside the primitive the patch name, which we don't really have inside our normal geometry. So let's start modifying the p-scale. Inside the first subsolver, with the data name linked to the geometry, I import with an object merge my wire, original wire, the one that is still not deformed. And I deform the same deformation that I did inside the object, inside subs. I just do it here inside dops. But I do it inside a for loop. To create this for loop, I import the dop geometry, which is our geometry. I transfer the patch name attribute from points to primitives. And then I run the for loop based on this patch name attribute under primitives. This will loop over each one of my worms. So for each worm, I will be able to create a different deformation. And I do that by changing the offset value. This offset value, I change it based on the iteration value of my for loop. To see the expression, I will show it here. It's a very typical way to create iterations, variations within a for loop. Once that I create this different deformation, I just basically copy the p-scale attribute to my dop geometry. And the output will be my updated p-scale attribute inside dops. Now we need to update the constraint geometry. To update the constraint geometry, again in the subsolver and the data name, be sure to include the constraint geometry. That way we will manipulate the constraint geometry, not the geometry of the Vellum solver. Here is the same principle. We create a for loop based on the patch name attribute, but as the constraint geometry has the patch name attribute inside primitive, we don't need to do the attribute promote. Now we do the same deformation as we talk, with the same offset based on the iteration attribute of the for loop. And now we use the Vellum rest plan. Normally, the Vellum rest plan requires a geometry, as it is done in order to create these deformations. Nonetheless, we're just updating the information of our constraint geometry. So we can just link our Dop geometry into the constraints input and our deform geometry into the rest geometry input, outputting only the constraints because we're only interested in updating the constraint. Once we have that, our constraint geometry is updated each frame and our worms will be working. To preview it, let's just play it. Now we have a worm race, but they're rather sad. They need to wiggle a little bit more. For that, I just add a pop wind force. I find with the interaction of gravity, the deformation of their body, plus the wind force and the interaction between them, that gives randomness enough that it looks natural. And you can increase this as many worms as you want. And that's really it. Once that we have this animation, this simulation done, we just need to import the Dop geometry into subs. We import it, we resample it, add the polyware exactly as before, give it a normal just in case, and the geometry is done. And here are our worms. Nonetheless, you don't really need to recreate the worms after you import the geometry from Dops. You can also use the wires as a skeleton and project whatever geometry you have as worm into the lines, but that's really beyond the scope of this tutorial. Well, I really hope you find this information useful and that you can apply at least some of it into your own projects. Till next time, I guess. Bye bye.